All right. Just roll right in. All right. All right. Okay. So I also have a lot of slides. I added like 6 slides because of Rusty Russell, so blame him when this also goes a bit long. But it's good. It's worth it. So I'm going to blaze through some of my slides. Forgive me when I skip some important things. And then we're going to go a little slower on some of the new slides that are based on what Rusty was talking about with the script restoration project. So, but the general topic here is Quirky Covenants. We're going to use and abuse some opcodes to make cool things. And who am I? For those who don't know, I'm that guy on the Hellbird site. I work at Swan right now on self-custody things. Swan is awesome. Use Swan Vault. That's my pitch. So here's the things we're going to talk about. When we're talking about covenants and scripts and things we want to build, a lot of us want to get better vaults. And there's been a lot of talk in the last year or so about some of these opcodes like CTV or APO, which is a sick hash flag. Lightning Symmetry is super useful. And then last but not least, how can you make OpVault do things it wasn't supposed to do? So if one thing I talk about LEnhance in this, there's a proposal I have to put those 3 opcodes together. I think it's a good way that we could increase Bitcoin script flexibility. So yes, when I say LEnhance, that's the 3 things I mean. Other terminology, for those who might have missed it yesterday, Rusty Russell talked yesterday about restored script. And this is the description of that in short words. So with restored script, you bring back everything that was in the original script, plus a few new things to support Bitcoin as it is today, and you make it safe. So that's the restored script in a nutshell. Okay, let's get right into it. What are vaults? What's the problem with the vaults the way they are right now? So vaults have been around for a long time. Originally, they were done with pre-signed transactions. You know, you put some Bitcoin, you make a key, you put some Bitcoin in that key, you pre-sign some ways to get that Bitcoin out that can only be spent maybe after some delay, and then you throw away the key you used to pre-sign that. Okay, so now you've got a thing in a vault. It's very safe because you don't have the key anymore. But for those who don't know, you can't actually delete keys. That's not a thing that you can prove has ever been done. And so you deleted the key, but maybe your stupid computer left it in some semi-volatile storage and someone could get it later when they steal your computer, right? So it's likely you can actually use pre-signed vaults, but kind of not. Okay, well, also we have, if we were to just put CTV into Bitcoin, you can make simple CTV vaults. This is something that James O.B. originally wrote, and these are cool, but they also have problems. You have to have a separate hash for each UTXO, or for each size of UTXO you want to deposit into your CTV vault. And that's kind of a weird, tricky thing where if you make a CTV vault and then you deposit the wrong size UTXO, it could be stuck there literally forever. It just burned Bitcoin. So that's kind of a problem. And with both of these, there's some data that you have to hold on to be able to spend the things. You have to have the transaction pre-images for CTV. That's maybe easy. Those could be something you could regenerate. The pre-signatures, if you lose those pre-signatures, money gone. All right. Can we make better vaults? Here's where I'm going to start blazing through some of the stuff here, because I think you can make better vaults with LEnhance, with check sig from stack, and Taproot and check template verify. And this is how it would look. There's a couple different ways you could structure this. There's 2 different ways you could make the vault output. One would be using, I'm using descriptors on this one. I don't use them later. Sorry about that. But the short version of what this slide shows is that you can make a kind of vault using 2 different variants of vaults, using check sig from stack that have, I think, usable properties for people that could actually use vaults. Because simple CTV vaults, they're not particularly usable. Pre-signed vaults definitely not very usable. But LEnhance vaults, the key thing here is that with a LEnhance vault, if you do it in the top way here, you can deposit funds to it. Then let's say you have your safety key, like, I don't know, you're split between 2 countries. You can go visit one of those keys. You can pre-sign some ways to get the funds out of that. And then when you visit the other key, you can all co-sign, and now you have an active vault. In the meantime, before you visit your keys, the funds are just locked to those keys, which is kind of fine. They're in your super cold wallet. But if you kind of periodically visit your keys, which is often how I think people in practice use cold multisig, they've got the keys distributed, say like, you know, one is in a safe in their house and one is in a safe at their best friend's house that they visit twice a year. So twice a year, you have an opportunity to update your vault for new amounts, for new UTXOs, whatever you need to do using this kind of a post-signed vault system. Also, with this, once you've signed for a UTXO of a given amount, you can deposit more UTXOs of that amount and withdraw them. So that's kind of the idea behind this design of vaults. I think I talked about a lot of what I said on here. Yeah, so I'm going to skip most of this slide. But here's the summary. Depending on the user's needs, these can provide a permanent situation, permanent reactive security, where you have a deleted withdrawal key that's kind of like the pre-signed vaults, but with better properties. Or they can have that you can revisit your vaults situation, revisit your cold keys and update your vault repeatedly. And I think that those two are usable for different people, depending on their needs in a vault. You know, like an institution might use one and an individual might use another. So I thought, since lenhance is now active on MutinyNet, this could be fun to build in a hackathon. I have at least the basic scripts here in this presentation. Okay, I added this recently, so forgive bugs. This is, I wanted to see how close we could get to emulating opvault with Rusty Russell's restored script that he was talking about, because I really like restored script. So I really want to see, you know, what's the limitations of this. And I immediately found out, and then talking with Salvatoshi, found kind of there's some limitations in doing vaults with this, but what can we do? Well, this is what it takes. One thing that is annoying about this, at least if you're me and you've been fighting with cats for a long time, is that it takes several cats. And, you know, that hurts my soul. But what is very nice about it is that it's a bit of a big script. We use several of the new transaction field selectors that you would use with ATX hash or optransaction ATX. And by using those, we're able to make very clear assertions about what's happening. So this script may be a little bit intimidating at first, but if we look at line 2, we're getting the single output, which is just the transaction output script pub key and amount. And we're verifying that the script we built on the previous line, which has the input amount in it, matches that. And I think that is basically makes explicit some of the automatic amount stuff that opvault does under the hood. I should have put a slide in about what opvault does under the hood before we did this. So, oh, that's right. Opvault is coming up next. So like, yeah, watch these back in reverse, and you'll be better prepared for this talk. So opvault automatically does amount computations to make sure that all the value travels from the inputs to the outputs within the vault or back to the vault itself. And so this does kind of the same thing, where I grab the amount from the first input and I make sure that it goes to the output. The downside of this kind of structure here is that it can't combine inputs the same way that opvault can. But I think that's okay. If you're going to use a vault, you're going to put big UTXOs into your vault. And so maybe in a real case, you're going to have like 1.1 inputs per unvault. Yeah, Christian.
Well, the restore script actually, part of the proposal is also iteration over.
Absolutely. If we go that far. Yeah. Yeah. Christian points out that if we go all the way with restored script, as Rusty mentioned, we could also add iteration over inputs. And if we did that, then we could do the full vault with restored script. I personally expect that we won't. We'll stick to restoring it more than expanding it when we do this restored script project. And in that case, we'll be limited in this particular way. But again, I think, raise your hand if you disagree, that vaults are going to be used with fairly large UTXOs. So the more common case is you're going to want to put part of the UTXO back, not that you're going to need to move value from several UTXOs out. Okay, so that's... Oh, right. Yeah, totally. So the steel transaction costs more in fees. Yeah, absolutely. This is the simple script. This is the recovery script for a restored script vault. So this is what you use when you're sending all the value from some UTXO to your safety key, whatever your safety key or your recovery SPK in this case might be. And I mean, how exactly a user might structure that, you could actually put kind of a safety key both as your taproot internal key and also the place this goes in that event. Again, people can use this in various ways. That's one of the suggestions that James has on his opvault BIP. Here's the locking script for the vault itself. This one gets a bit uglier. There's a god-awful lot of cats up on that slide. The thing that I really want to point out about this basically there's two parts to this script. One is building a tap tree in script using restored script. As you might expect, that's somewhat similar to building a tap tree in cat script, as Rindal does. It's basically the same structure, except we don't have to do quite as many cats. There's still, I didn't actually count them, there's like still 10 cats in this script. Rindal uses about 20 cats per introspection. We have 10 cats here, so there's a lot of cats floating around this room. But the point is we build up a new Merkle root for a tap tree, and then we verify basically the same thing, that all of the value coming in from the inputs goes to that tap tree that we built. So the bottom part here is very similar to the recovery script, which is why I put that one first. And again, and the result here is that when you run this script, it creates an output who can be spent either to the recovery script we just saw, or using something delayed by that 18 CSV up at the top. And I used Rusty's invention, opsegment, in this, because that way I can take a full script straight from the spender and not worry about an op success being thrown in there and ruining my vault. So this is why, a concrete use case for why Rusty suggests adding op segment, because we have op success now. When you didn't have op success in original script, you didn't need op segment, but now we have tap script with op success. We need op segment so that we can simplify these things. Whereas with op vault has to avoid that. You have to pre-code the script fragment and just take arguments for it from the stack. Because otherwise you would risk having just pushes, pure pushes rather. Because otherwise you could risk an op success being thrown in there. Op segment, the very top line of the script itself. 18 CSV op segment. Yeah, so what op segment is doing there is that in checking for op successes, we evaluate the script in segments so that I can say this precondition must be met. The 18 CSV must be met before you check anything else. And then if it can fail on the 18 CSV, and if it fails there, the script never executes. The rest never executes. If you get past the 18 CSV, then you check the rest, which could have op successes. And it could be that anyone can spend at that point. But the vault condition, which is that you must wait 18 blocks, 18 blocks still holds. And that's the important thing, is that you must wait 18 blocks before you spend this, because that gives me a chance as the vault holder, someone stealing it to an op success script. Why are they doing that? Because they're a miner, I don't know. But they're doing that, they're stealing it to an op success script. I can still recover it to my safety path. The segment protects me from it just being a full op success. Yeah, it did well. All the way to confirmed. Right, because you confirm an output to a script with 18 CSV op segment as the spend script. Yeah. So for 18 blocks, I have a chance to send it to my recovery. And again, that's very similar to what op vault does. So watch the next talk, and then come back for this one. Okay, so this is pretty cool. The downside of this is it is a bit bigger than using op vault. I kind of guesstimated and hand waved. That I think it's about 8 VBytes larger for op vault when you're doing withdrawal, and 16 VBytes more total when you're doing a recovery. So this is more expensive than op vault, but you can build it in just restored script without a specific vaulting opcode. So I thought that was cool. Yeah. The other thing I wanted to mention here is that it's a little interesting that James made a design goal for op vault that you can do a partial UTXO unvault. Especially because he was kind of designing around check template verify. If you have check template verify as part of your kind of withdrawal path, it seems reasonable that you would just encode change back to the vault in that withdrawal path as the CTV. So once the vault is successfully withdrawn from, some change comes back to the vault. You don't really need to do a partial withdrawal. It is very important, or I should say it's at least somewhat important to be able to combine UTXOs in the withdrawal, but I think it's less important to be able to split UTXOs in the withdrawal because of that change via the CTV. Any other questions about restored script vault? Yeah, Tidwell. That's a great question. So Tidwell asked about fees in this, and it's the same thing. this design of restored script vault is exactly trying to replicate James O'B's op vault. There's probably something better you could do with a stored script around fees. In that, it's always bring your own fee. So one thing about the way these scripts are written is that they look only at a single input or a single output at a time, which means that you're unvaulting and all of the funds, 100% must go from here to there to prevent any kind of fee theft. That means you have to add fees separately. So you have to have a separate hot wallet that you're going to add an input and an output from to do fees for this. Or you need or you need TX sponsors, or you need something else to get fees into this. This design does not cover the fees within the protocol. Yeah, Lolo. Correct. Yep, exactly. So this lets you, like I said, visit your safety key, whatever kind of structure your safety key has, visit it periodically, sign new ways to withdraw from it, and create kind of updated vault withdrawals each time you visit it. Yeah, so that's one of the powerful things about checksig from Stack. One of the reasons I like it is that you can do delegations with it. If you have checksig from Stack and cat, you can do combined delegations. You can be like, this delegation becomes valid after this time lock, because you can encode the time lock and cat them together and check that. So yeah, delegation is one of the functions you get with checksig from Stack that I use here. Yep. Yeah, good observation. Okay. Any other questions on vaults? Otherwise, I have Lightning Symmetry up next. All right. Yeah. MutinyNet has lenhance on it now. It has CTV, checksig from Stack, and internal key. So this vault can be built on MutinyNet right now. It's just Mutiny wallets or Ben the Carman's Signet. You can use it. That's all it is. It's not the new anything. It's just its own thing. At least that's my opinion. Ask Ben. All right. The next thing to talk about before we get fully into Lightning Symmetry is just a little bit about any prev out versus lenhance versus CTV, because it's kind of important input data to how we're going to build Lightning Symmetry here. So here's just kind of a highlight of what's different and the same between check template verify and sig hash any prev out, sig hash all. What's hashed? The green things are the same. The blue and yellow are different. And what you'll notice about what's different is that it kind of doesn't matter in a lot of cases which one of those two things you get signed. So yeah, that's just a quick note there. The one thing that is maybe useful about check template verify relative to any prev out, any script, all here, is that check template verify can constrain future TX IDs, and any prev out cannot. That matters not for LN symmetry, but it matters for some things. So, it still does not constrain TX IDs. There's still malleability in there. So CTV, one of Ruben's like fundamental designs for it was that it could constrain TX IDs, and so he added the sequences, what's that? It's the input side where the TX ID can be malleated, because yeah. So anyway, that's just. It just is what it is. Depending on what we're doing in the world of Bitcoin, you could update any prev out to constrain TX IDs. But you do care about them if you're doing something like ARC, because you want to have predictable TX IDs that can be used in a connector for some other use case. They need to be predictable because you're creating an out point. It doesn't work the same. It doesn't work the same. I've tried. Sorry, I'm not repeating what Lalu is saying here. Lalu is saying that because APO signatures are rebindable, you don't need TX IDs to be stable, which is why it was designed that way. However, in the fullness of kind of the intervening 7 years since it was designed, there's been new ideas of connecting by TX ID specifically using an out point, because then you have a consensus rule that ensures there can't be another one that satisfies that. And that's what's important about that. That wasn't kind of in the mind share when APO or no input was being designed. So there's reasons that these things are the way they are. Restored script. We're going to restore script. And restored script includes TX hash as the sig hash modes, and it's going to be amazing. Okay? APO is not dead. APO is evolved. Yeah. This slide's not important. All right, let's talk about how we can build Lightning Symmetry. What is Lightning Symmetry, and what does it take to build it? So Lightning Symmetry, for those who don't know, is a way to do Lightning channels where instead of, if someone force closes a channel with an old state, instead of being able to penalize them and take all of their funds on the channel, instead you can simply advance the state to a later state. And that advancing process can be done repeatedly until no one has a newer state. And the other property of Lightning Symmetry is that the state is symmetric. In the existing Lightning channels that are deployed today, each party has a different set of revocations because you have to be able to revoke each previous state to correct a channel state if someone force closes with an old state. With Lightning Symmetry, everyone has the same states going along, and whoever has the latest one can just always update the channel to that state in the event of a force close. What does it take to do that? You need to have rebindable signed commitments for the channel updates, because you don't want to have to go through every single state. You don't even want to have to store every single state. So let's say the channel closed, it had 10 updates on it. I force close it and I put state 5 on chain, but you have state 10. You shouldn't have to remember states 6, 7, 8, and 9. You should be able to just put state 10 directly on chain. That's why you need rebindable commitments. They have to be able to bind onto any state in that sequence and get to the latest one. And then Greg Sanders, InstaGibbs, actually wrote down a full implementation of Lightning Symmetry and found that you can save a signing round trip, which is pretty important, especially for rapidly updated channels, if you can ensure that the update transactions communicate enough information to allow the settlement path to be encoded in the updates. The original Lightning Symmetry the original Lightning Symmetry design, which was called L2 at the time, used an extra round of signing here so that it was a signed update to the settlement, or signed settlement. We can avoid the signed settlement, avoid that round trip, if we can communicate the settlement data somehow to allow that state to be updated. The details of that will become more clear in the scripts. So the numbers here are not important. I mostly put them there to show that to show my work on the numbers I'm going to show later comparing these. Okay, so we have 5 1/4 kinds of Lightning Symmetry. First one, the original way that Greg Sanders did it, you use just check sig operators. Stuff we know already, you're just using a different key length. So that's why I put the 0, 1 key and G there, because we're using 33-byte keys that are the TapScript key version 1. And there's a weird thing in here for those who are familiar with how taproot witnesses look, and that is that we have an annex. So in Greg's design for Lightning Symmetry, he used the annex to communicate that settlement hash and avoid a round trip of signing. But this is cool. And here's the sizes. Here's the red on the bottom there, the total witness size. And the green is the total vbytes to do a unchallenged force close and a challenged force close. I'm guessing I missed a byte or two here or there, but I think I got it very close. All right, so that's any per image. That's the original. Those scripts look really nice. Here's if you do any per and CTV. Those scripts are even nicer. We just have a settlement hash and a CTV. We don't have that weird, we get rid of that 0, 1 concatenated with the G, the generator point there. We just have settlement hash because we no longer have to kind of do the any per signature to get CTV-like behavior. We just have CTV. So that's cool. Sizes get a little bit smaller. What happens if you try to do it with L-enhance? Just L-enhance. Just L-enhance is kind of bad. It works, but it's kind of bad. We've got to do 2 signatures because we need to get that settlement hash still on the chain somehow. That settlement hash is needed in order for someone later to bind to that and spend it. They have to know what the content of the script were. And without that settlement hash, they can't generate the script to know what to sign in order to update it. Okay, so we have to do 2 signatures. This gets big. But the thing I want to note when we look at the fact that this gets big All right, so it's 330 and 612 witness bytes there versus 238, 414. That's a huge difference. But the V bytes, they're not that different. 731 to 781, it's 50 V bytes. It's kind of a lot, but it's not even 10%. So this is bad, but it's not that bad. What if we had L-enhance and cat? Well, that's better. Instead of having the two signatures, we just concatenate the two pieces of data we needed signatures on, and then check a signature on them. There's one really important thing about doing L-enhance cat symmetry here, and that is that you have to either check the length of or hash, one of the two things you're going to concatenate together before you check a signature on them. Because otherwise, a malicious user could move bytes between them and make CTV check nothing. Because CTV is a NOP if its input is any length other than 32. But that's fortunately easy. You throw a SHA-256 in there, or a length check. That's what I use the SHA-256 because it's a smaller script. And we get this. This is very comparable to APO symmetry. I forget the exact, there's a table at the end. And then we have restored script symmetry, which I really like. Restored script symmetry, because we can use TX hash, and we know TX hash will give us a 32-byte output. We're not using CTV to check a hash. We get a 32-byte hash, and then we check a signature against that hash that we get with TX hash. We can just cat with the settlement hash. It's safe. No matter what length of settlement hash they give us, if it's not what we chose to sign, they can't move bytes around and have a valid signature. So restored script symmetry looks like this, and it just works. So settlement hash comes in on, down here. It comes in from the witness there, which is the same basically as L-enhanced symmetry. It comes in on the witness there as well. Signature, settlement hash, signature update hash. Exactly. So Lalu asked, is the settlement hash there to allow clients to be stateless and not remember any state from each update? And that's exactly what it is. In order to keep the data storage on each channel partner of one, each partner needs to be able to update from any state to the final state that they have. And they'd have to store that settlement hash for each state unless it's communicated by the transaction putting an update on the chain. And, say again? It's the settlement transaction. So the settlement transaction, Lalu asked what the preimage for the settlement hash is. It is the settlement transaction itself. So settlement transaction outputs are what matters here, right? Because we're defining how we split the channel balance between the two parties. And so the settlement hash is the CTV hash concerning the outputs for that settlement transaction. And because we're trying to avoid this extra signing round trip where you could make a a fixed script except for the CLTV changing at each update if you didn't put the settlement hash in the update script. But in order to avoid a signing round trip, we need the settlement hash somehow in the signing script, in the update script. And once the settlement hash is in the update script, we need to have a way to communicate that settlement hash on chain so that it can be updated later. And this is, I'm guessing not everyone has picked that up because it took me several conversations with Greg to understand what the heck he was doing with the settlement hash as well. But eventually I got it. So, ask me later and we'll sit down and talk about it if you want to. All right. The last thing I wanted to say is, and I said this in the panel yesterday as well, everyone says cat can do anything, and this isn't something that I have been pushing back on for like 6 straight months now. Cat cannot do anything. It can't do lightning symmetry. But I kind of wonder if it can kind of do something almost like lightning symmetry. I'm trying to get Randall to try and build this so that we see what it looked like. So if anyone wants to like poke at him, be like, go, build cat-ish symmetry. Because you can't do rebindable signatures with just cat, right? That's just not something it does. We don't have a way in Bitcoin right now to do rebindable signatures. They all bind to at least one UTXO. And so that's it. That's what they do. But because they all bind to at least one UTXO, I think using just cat, you can use two signatures that do bind to a UTXO, have your channel start with two channel outputs, and that gives, there's like one of those kind of a dummy output that allows a later party to do one update. So it's not true symmetry where we can update many times. So it wouldn't work for multi-party channels, but for a two-party channel, you only need one update at most. You get, the one liar and then the one update, or the one bad backup and the one update. So I think you can do cat symmetry with two bound signatures using two UTXOs. But of course, we don't want Lightning with two UTXOs per channel. Yes, Arik. Arik's asking, why can't we use the cat trick, where you use the witness stack to constrain certain parts of the transaction, and then fill in just the parts we need to constrain in our cat script to create something like Lightning Symmetry. And the problem is that we still need to have some signature to authorize each of those cat scripts to be on this channel. And that signature is going to bind to a specific UTXO, so then we can't update it to another one later because we don't know what that UTXO is going to be at the time that first update is made. So we can absolutely have an updatable channel that uses signed updates based on exactly what you described, Arik, to get to a state that's a correct state for both parties on the channel. But what we can't do is then correct that without a separate UTXO that inputs to the correction. Right, that's what no input is. Yeah, so cat needs rebindable signature, or sorry, I can't talk now. Lightning Symmetry, thank you, needs rebindable signatures. And so you need no input, or you need CTV with chuck_sig from stack, or you need some just other new SIG hash, like the TX hash as SIG hash. You need some way in Bitcoin to have a signature that can be rebound between two different UTXOs. And as soon as you have that, you can build Lightning Symmetry. And that's part of the point, by the way, of why I showed you all of these ways to build Lightning Symmetry, is like, now that I've dug in with Greg and talked about it for a long time, it turns out it's really easy to get Lightning Symmetry. We need one little tiny thing. We need to be able to make a rebindable signature, and we can get that from anywhere. It just needs to be rebindable. Okay. So that is about Lightning Symmetry. Here's the comparison I mentioned I would have at the end here. And what's salient about this is not so much the specific numbers, and there's a reason I didn't color code them in any way. It's really that we can get Lightning Symmetry in all of these ways, and the numbers are basically the same. Even the worst one, L-enhance here, it's just a little bigger. This is for forced closes. Forced closes are expensive. They've always been expensive. They're always going to be expensive. And the difference is here, it's a 10% range. Not even quite a 10% range. So whatever way we get Lightning Symmetry, we should really get Lightning Symmetry. Please? So. Yeah. So I'm glad that we have agreement that we should get Lightning Symmetry at some point. Please. All right. Last part of my talk here, and I think it's like a very short break since I'm going over time as well, is Vault fun. And the reason this part is in this talk, and the reason it's Quirky Covenants, is that even when you try to design a very specific purpose thing in Bitcoin script, it can be used in lots of different ways. And I wanted to emphasize that. Someone was joking about how everything enables hash rate escrows. And I was like, I wonder if Vault can do hash rate escrows. Well, here's how Vault works in a very short thing. I should have put that earlier. Like I said, I rearranged the talk. Here is how you make hash rate escrows without Vault. It's not even that hard. Because you can, Vault takes arguments from the stack, and And one of the things it takes off the stack is the script that's going to be then used with the arguments. So you can make the script an argument to the script, and then you just propagate the script as long as you want. And now you can make counters because you keep using the same script over and over with new calls to vault. So that's what this does. So you can see the quotes on there that put this whole thing as just a string onto the stack, a byte string, and you copy that along with your op vault. Is it kind of a big script? Yes. Does it do hash rate escrows? Yes. Yeah, that's really all I wanted to say about that. There's comments on it if you're curious about how exactly it works. And hopefully the link to the slides will be up here somewhere on a website somewhere. If not, you can ask me for them. So yeah, I kind of mentioned part of why this matters. I have a speculation that there is a perfect correlation between anything that we can possibly do that will make true vaults, where you can have an output script you make, which must be spent with a time delay before it goes to its final destination, like that vault feature, that fundamental vault feature. I think anything that can do that must also be able to do hash rate escrows. So if vault is a feature that we want on Bitcoin, we must also build hash rate escrows. I think that's fine. I don't think any problem with that. Yeah, and I mentioned check contract verify here, although I don't think I want to talk about it right this particular moment. All right, any questions? Ryan. No. Okay. So when I got on the plane to come, so the question is, what do I think the best proposal is to get Lightning Symmetry, basically, right? Yeah. When I got on the plane to come here, it would have been lenhance. Lenhance is my proposal, which has check from stack, CTV, and internal key. After talking to Rusty, it's restored script. I want to restore the script. So I like both of those things. I think they're either one is fine. I think Rusty makes a really compelling argument that we're basically going about this the wrong way and trying to upgrade Bitcoin by doing the smallest thing that gets us the features that we want. Like, I really want Lightning Symmetry. I really want something like ARC or timeout trees. I really want some things. And I'm like, okay, here's like the simplest proposal I can do to get those things. And that's what everyone's been doing, right? That's why we have TX hash and we have cat and we have lenhance. And the right thing that we should be doing, and the argument Rusty makes very compellingly, is we should be engineering the best Bitcoin script, not trying to do the smallest thing that gets us the feature specifically that we want. And so that's why I've shifted, after talking to Rusty, from what I got on the plane here as my opinion. So, Lalu. Yeah. So Lalu's asking, what exactly is a hash rate escrow? How am I defining that for this purpose? A hash rate escrow, for my purposes, is something that can count down, as Paul Storks likes to say. It just counts down from a big number, and when it gets to 0, it releases something. And the reason you want to do that is you can have a thing that can only happen once per block. And if you don't have a lock on it to who advances it, then the person that's going to get to decide how it advances, up or down. That's why there's this yellow line on this slide. You have to be able to go up or down on the counter. And if there's no signature lock on this, the miners are who gets to decide what direction it goes. So it's a hash rate escrow. Whoever wins each block gets to decide which direction the counter goes. And at the end, if it never goes to 0, then you never get the funds. But if it eventually gets to 0, you get the money out. That's a hash rate escrow. That's the destination at the end if it gets to 0. Yeah. So hash rate escrows would protect withdrawals. Yeah. Rob. Oh, God. Yes, please. He makes a valid point. Sorry, Rob was relaying from a Twitter DM chat that apparently there's an error in my lenhance, plain lenhance ln symmetry because one of the signatures can be reused between updates, and therefore your channel partner could force close and lie to you, and then you couldn't spend the thing. So there's an error in my slides. You can't do lenhance symmetry the way I had it there. You have to use an operator instead. It costs like 4 more VBytes. Chris, you had a question? Okay. All right. Let's call it a wrap then. Thanks, everyone.